Hello dear friends, welcome back friends. In this video today we shall be looking at how we can get the moment of inertia of a uniform solid sphere of mass m and radius a about the diameter. So friends, please stay tuned and make sure you watch the video from start to finish. And friends, I'll beg all of you for one thing guys, please give the video a like because that does motivate me enough to keep this channel going. And friends, please share the video out with others so that they can have access to great contents like this. Thank you very much friends, and let's dive straight into our video today. Awesome friends, awesome. So guys, as usual, let's start by picturing how our solid sphere is going to look like guys. Let's start by looking at the Cartesian coordinates. Let's see, we have the vertical axis, we have the horizontal axis. Great. So guys, let's look at our sphere of this form. We have the origin at this point. Let's look at our sphere. Great. So friends, like I said in our previous video guys, we saw how we could get the volume of a sphere, right? In this case we shall be looking at how to get the moment of inertia, but we shall use the volume to get the moment of inertia. Great. So friends, let's put some labelings on it. It's going to have a radius, like we said, a. Here is going to be a, right? Then the distance now to the left is now going to be what guys? Negative a. That's the radius is going to be negative a, since if you take a minus a guys, it gives us 2a. Good. Okay, good. So friends, this is what we have. Then friends, let's put further labelings on them. We are going to have the x-axis at this point, because this is now going to serve as the length of each of the discs, because guys, once again we are going to be using the disc method. Okay, we are going to be using the disc method. Great. So friends, we are going to have this our y coordinates. Great. We have the y coordinates, that is the radius of the sphere. We have it as the y coordinate. Great. So friends, we are going to start by splitting the sphere into smaller similar discs perpendicular to the x-axis. Great. Like I said initially guys, we are going to be using the disc method. And how we approximate the volume of the sphere, we are going to use that same knowledge on how to get the moment of inertia of this our uniform solid sphere. Guys, in such a case, we are going to split this our sphere into smaller discs, okay, which are approximately the same sizes. Okay, they are approximately the same size. So we are going to make them very tiny as possible, such that they are approximately the same sizes, the same shapes, the same radius, everything guys. Okay, that's what's going to happen. Then after splitting all of them now guys, because they are going to it is going to take the shape of a disc, we can therefore get the moment of inertia of that our disc, and we sum them up. Great. Okay, we sum them up. Great. So friends, in our previous video we saw how we could also get the moment of inertia of a disc, right? Great. So we are going to use that same knowledge now to get that of this our sphere. So friends, we are going to split each of them such that they are going to have some. We are going to split them like this. Let's go ahead to split. Great. So that they are going to have some change in the x value. We can call that delta x. Great. And we are going to let our lambda to be the mass per unit volume. Okay, like I said guys, we are going to be using the volume to get the moment of inertia of this sphere. That's why initially we were able to derive a formula for the volume of a sphere guys. If you've not checked that out using calculus, make sure you check it out guys. To make it easy guys, I'll put a link to that video in the description for your convenience. Great. So friends, that's what we have now. So friends, now we know that the volume of each of these our discs guys was given as what guys? Was given as 4/3 pi r cube, right? In this case our radius is going to be a, that's why we have it to be 4/3 pi a cube. Great. So friends, since we let our lambda to be the mass per unit volume, therefore means lambda is equal to our mass is m all over the volume, which is 4/3 pi a cube. Great. So friends, in that light now, what we're going to be doing now is that if we arrange this our lambda so well, because the fraction here looks absurd, right? If we arrange it so well guys, we're going to have our lambda to be the same like 3m over 4 pi a cube. Great. That therefore implies guys the volume of this our sphere in terms of the mass, we are going to have the volume that is 4/3 pi a cube times lambda, that is equal to the mass. Okay, this is the mass of our sphere in terms of lambda. Great. guys, in such a case now we have the mass of each of the elemental disk that we are going to cut this our spheres into. Okay, we have the mass of each of the elemental disk. So now guys, we are now going to take the x-axis as a diameter. Then each of the elemental disks, guys, is going to have a radius of a and thickness delta x, or change in x, guys. You can picture it so well, because if we take the x-axis, guys, to be the diameter, right? The x-axis normally is our diameter. Okay, that therefore means that, guys, the distance between the center of each of the discs we are going to cut and any point along the disc is going to be y. Okay, that is going to be the radius. Great. So friends, we should also keep in mind that the volume of each of those our cylinders, or each of those our disc, is going to be v equal to pi radius squared times the height. Great. Guys, in that light now, we can therefore see that the volume of each of these our small disc that we are going to form is now just going to be v equal to pi y squared, since our radius is y. Then now the height, guys, is simply going to be what? Delta x. That's a small change in the x value, which is the height of each of the disc that we are going to create. Great. So we have that, guys. That would therefore implies now that the mass, since we have that the mass is given as the volume times lambda, this is now going to be, this is the volume. Okay, so we are going to multiply everything by lambda to get the mass. We are going to have the mass to be approximately the same as, guys, the volume. We have the mass to be the volume, which is all we have here, times lambda. Great. That is what we have, guys. Then now, friends, the moment of inertia of each of the discs, now the moment of inertia of each of the discs is simply going to be 1/2 times the mass times the radius squared. That is what we saw in our previous video, right? That the moment of inertia of a disc is given as 1/2 times the mass times the radius squared. That therefore implies, guys, if we apply the same principles, we are going to have the moment of inertia of each of those our discs to be given as 1/2. The mass is as we have here, we have pi y squared delta x lambda. Then the radius squared, like I said, guys, is simply the y. Okay, it's simply going to be y. Great. That's what we have, y squared. Great, friends. That's what we have. This is for an elemental disk, just for one of these our disc. Then now, guys, for the whole sphere now, for the whole sphere, we are going to sum up all of the possible moment of inertia that we are going to have of each of the individual discs, which is going to be the sum from negative a. That is, we are summing from negative a up till the point a, that is the entire sphere, from negative a to a, of just 1/2 pi y to the power 4 lambda delta x. We are now going to change now from continuous now to discrete. This is now going to be the definite integral, now going from negative a to a of 1/2 pi y to the power 4 lambda dx. Great. That's what we have, friends. Then now, friends, we should not forget that we are going to we can picture this our disc, right? We can picture this our disc, friends, to just be like a circle whose radius is a and whose center is at the point 0, 0, right? And the equation of that circle, guys, is simply going to be y squared plus x squared equal to a squared, right? So if we make y the subject, guys, we are going to have the integral going from negative a to a of just 1/2 pi. Our y is squared is simply going to what, guys? A squared minus x squared. Keep in mind that the equation of this our circle, guys, is simply going to be x squared plus y squared equal to a squared. So make y squared the subject, we are going to have a squared minus x squared, all that still squared times lambda. Then we have the dx squared. So friends, if we simplify further, guys, we are going to have 1/2 pi lambda. Since they are all constant, they come out of the integral. Then we have the integral going from negative a to a now of expanding what we have inside, guys. We have a to the power 4 minus 2a squared x squared plus x to the power 4 dx squared. So integrating each of them now, guys, we are going to have 1/2 pi lambda into a to the power 4x minus 2/3 a squared x cubed plus now 1/5 x to the power 5. Great. That's what we have, friends. The limit of integrations are going to go from, we have from negative a, and they'll be ending at a. Good. That's what we have. Then, friends, if we plug in everything, guys, we are going to have 1/2 lambda 1/2 pi times lambda into we substitute our a into all the x's. We have this, putting negative a, guys, we have negative into the upper limit is negative a, everything takes negative. Good. So this is what we have, friends. So if we simplify a little bit further, we are going to have what we have here. We have 1/2 pi lambda into 2a to the power 5 minus 4/3 a to the power 5 plus 2/5 a to the power 5. Great. And friends, simplifying everything so well, we are going to have 1/2 pi into, keep in mind that our lambda is given as what, guys? What's lambda? 3m/4 pi a cubed. That's why we have it here. Then, guys, simplifying all of this, we have 16/15 a to the power 5. Friends, simplifying everything simply gives us our answer to be 2/5 ma squared. Great. Friends, that's the moment of inertia of our disc about the diameter. Okay, that's the moment of inertia. So friends, thank you very much for watching the video. But friends, just have a quick remark here. Let's just have some quick remark. Let's be looking at the integral going from negative a to a of 1/2 pi y to the power 4 lambda dx. Guys, let's observe. Let's do some observations, guys. We notice that this is a definite integral, friends, going from negative a to a, right? Of, you can see that our function here, 1/2 is a constant, pi is a constant, lambda is a constant, guys. The only variable here is just y to the power 4, right? And it is an even function. So friends, when integrating negative of a value to the positive of that same value, as far as your function is an even function, guys, it is simply given as 2 times the integral of that same function, but this time around going from 0 to a of that same function. Okay, so we could use that same knowledge here. It's going to give us the same answer. So friends, try it. If it's the same answer, guys, put in the comment section down below. If it doesn't, still put in the comment section down below, and we're going to be looking at what to do. Okay, but it will give you, these are the properties of definite integrals that we all know, especially that concerning even functions. So friends, thank you very much for watching the video. Thank you so much, and feel free to put your worries in the comment section down below, and I'm going to reply to them as soon as possible. Have a blessed day.